Hello, I am Matti van Oef and I'm going to present the paper Dragonblood, analyzing the Dragonfly handshake of WPA3 and EAP PWD, and this is joint work with E.L. Ronan. If we look at the history of Wi-Fi, we see that initially they relied on web for security. Unfortunately, this protocol was quickly shown to be completely broken, and in response to this, they released WPA, which was based on a draft of the IEEE standard. Once the IEEE standard was finalized, the Wi-Fi Alliance released WPA2. Unfortunately, this algorithm is vulnerable to offline password brute force attacks, and recently it has also been shown vulnerable to key reinstallation attacks. In response to these two weaknesses, WPA3 was released, which internally uses the Dragonfly handshake. And the Dragonfly handshake previously was also used in EAP PWD. And EAP PWD is an authentication algorithm that is used in a low amount of enterprise Wi-Fi networks where you authenticate using a username and a password. And Dragonfly is what we call opaque, and it provides the usual properties. It provides mutual authentication and it negotiates a fresh session key. And more importantly, Dragonfly defends against offline dictionary attacks, in contrast to WPA2. So how does the Dragonfly handshake work? Well, before executing the Dragonfly handshake, the password, which may be stored in ASCII or in Unicode, needs to be converted into a so-called group element P, and this group element can then be used in the cryptographic calculations of the handshake. And once this is done, we can execute the commit phase of the handshake, which essentially negotiates a session key. After this, the confirm phase is executed, which confirms that both peers negotiated the same session key, and this also proves that they both possess the password. Now, the important question here is how can we derive P from a password? And how this is done depends on which specific cryptographic group is used in the Dragonfly handshake, and in our case, and in this presentation, we will focus on elliptic curves. So the question becomes, how can we convert the password into a point on the elliptic curve? And this is generally done using a hash-to-group function. And one naive way to do this is to simply hash the password together with the MAC addresses of the client on the access point and use the resulting value as the x-coordinate of the point on the elliptic curve. Unfortunately, not all x values lie on the curve. In particular, only half of the x values lie on the curve. For the other half, we need to find the solution. And what did the designers decide to do? Well, they included a counter in the hash function. And in case the x value does not result in a y value, in that case, we simply execute a new iteration with the counter incremented by 1, which results in a new x value that hopefully does lie on the curve. Now, some of you may already see the problem here. The problem is that the number of executions that are performed by this algorithm now depend on the password and also on the public MAC addresses. And perhaps what's most surprising is that the IETF and the CFRG warned that this will create side channels in the algorithm. Unfortunately, the designers discarded these side channels because they thought they were theoretic and that they would not leak the password of the network. Unfortunately, this side channel does allow an adversary to perform an offline dictionary attack. So how can we recover the password based on the number of iterations that are executed? Well, we have two attack scenarios. The first attack scenario is that we can act as a malicious access point and we can induce clients into connecting to us, or we can pretend to be a malicious client and attack an access point. In both cases, we will measure how many iterations that the other device is executing. For example, if we attack an access point, we will spoof a client MAC address of A, and let's say that we can measure how many iterations the access point is executing, and in our example, it is executing 2 iterations. We can then execute the hash to group algorithm offline for the passwords in our dictionary, and we can then exclude passwords for which the number of iterations do not match our observation. Now, unfortunately, using one MAC address is not sufficient because it does not filter out all passwords in our dictionary. In our example, 2 passwords are still possible. So we need more information. Now, where do we get that information? Well, if we look at the algorithm, we can see that the MAC addresses influence the execution of the algorithm. So what we can do is we can spoof a different client MAC address and again measure how many iterations that the access point executes. For example, we can spoof MAC address B. We can measure that the access point now executes 1 iteration. We again execute the hash-to-group algorithm offline, and we can exclude passwords that do not match our observation. And we continue spoofing MAC addresses until we uniquely determine the password of the network. So what is the complexity of this attack? Well, let's say that we want to uniquely determine the password in the RockU database dump. Then on average, we will need to spoof around 17 MAC addresses. And this results in a fairly efficient algorithm. And one of the main takeaway messages here is that the number of iterations that are executed for a given set of MAC addresses forms a signature of the password. Now, there is one thing that I haven't explained yet, and that is, can we indeed measure how many iterations that an access point or a client executes? And to answer this, we attacked a Raspberry Pi 1B, which was running an open source implementation, and we measured whether we could determine the number of iterations that are executed. And it turns out this is fairly easy to do. Against an EAP PWD client, we only need 30 measurements to determine how many iterations are being executed when we use Crosby's box test to filter out noise. So that covers the case of the EAP PWD algorithm. When they standardized WPA3, they did realize that this algorithm had some side channel issues, and they tried to prevent them. And the first thing they did with WPA3 is they always made the algorithm execute 40 iterations and return the first X and Y coordinate that lies on the curve. On top of that, they checked whether the X value is on the curve using a blinded constant time test. Additionally, they executed the extra iterations using a random password, again to reduce the chance of any possible side channels. Now, there is still one remaining problem, and that is that the hash output has to be truncated to the size of the prime P. So, for example, let's say that we are using a 256-bit elliptic curve, then the output of the hash function is truncated to the first 256 bits. However, this truncation is not always sufficient. In particular, if we use brainpool curves, then even if we truncate the hash output, there is still a high chance that the resulting X value is bigger than the prime of the curve. And we want to avoid that because it introduces a small bias into the subsequent cryptographic calculations. So how did the designers decide to tackle this issue? Well, they used rejection sampling, which basically means that they included an if test to check if the X value is higher or equal to the prime, and if so, they simply execute another iteration. So now the question is, are all side channel leaks avoided? Unfortunately, they are not. The problem now is that this piece of code may now be skipped in an iteration. And more problematic is that the number of times that this code is skipped depends on a password. Now, this case is not as trivial to abuse as the EAP-PWD case, because the number of times that this code is skipped depends on the real password, but also on the random password that is executed in these extra iterations. Nevertheless, we were able to extract enough information to perform an offline dictionary attack. And the way we did this is by realizing that the variance of the execution time still depends on when the password element was found. On top of that, the average execution time depends on when the password was found and on the average number of iterations where the highlighted code here was skipped. So now the question is, can we measure these things in practice? And to determine this, we again performed an experiment against a Raspberry Pi that in this case was running an open source implementation of WPA3. And here we had to make more timing measurements per MAC address. We had to make about 300, but with these measurements, we again have enough information to perform an offline dictionary attack against Dragonfly. Now, apart from timing attacks, we also discovered cache attacks against implementations. These attacks are executed by setting up a malicious access point and tricking clients into running unprivileged code. This can, for example, be an unprivileged Android application. The advantage of our cache attack is that they work even when the victim is using NIST elliptic curves. This is because our timing attacks are not possible against NIST curves, because there the X coordinate is very unlikely to be higher than the prime P of a NIST curve. However, using our cache attacks, we can monitor when the password element has been found using the flush and reload technique. And to know exactly in which iteration the password element is found, we also use flush and reload to monitor when the hash function is executed. And combined, this allows us to tell whether the password element was found in the first iteration or in a later iteration. The key takeaway message here is that our cache attacks again form a signature of the password, which can be used to brute force a dictionary. And we implemented the brute force algorithm on GPUs, and here we found that if you take any dictionary or any password leak, then we can brute force it for less than $1 on Amazon instances. And even if you want to brute force all 8 symbol passwords, then the cost will be higher, but it's still doable in practice. We also discovered several Wi-Fi specific attacks. The first one is a simple denial of service attack, and this is caused because every run of the hash-to-curve algorithm has to execute 40 iterations, and this is computationally quite expensive. Apart from this, we discovered a downgrade attack against networks that supports WPA2 and WPA3 at the same time. And against these networks, we can trick a client into connecting using WPA2. And even though the handshake of WPA2 will detect the downgrade, the partial handshake that got executed already leaks enough information to perform a dictionary attack against WPA2. Additionally, because Dragonfly can be executed using multiple elliptic curves, it is also possible to perform a downgrade attack where we trick the access points or the client into using a weaker elliptic curve than they normally would. So how did we disclose these results? Well, we initially contacted the Wi-Fi Alliance, and they privately created security guidelines on how to avoid our attacks. These guidelines also recommended the use of brainpool curves, but unfortunately, as we have shown in this presentation, these are vulnerable to side channel attacks as well. In response, at the end of last year, they released new security guidelines that now prohibit the use of brainpool curves. Their guidelines are rather vague though. For example, they mention that implementations must avoid side channel leaks. However, this is hard to do without more explicit guidelines. They also say that if WPA3 in transition mode doesn't meet the security requirements, then basically don't use it. In other words, they don't address the underlying issue. Another downside is that fundamental issues are still unsolved. Namely, it is simply hard to implement Dragonfly in constant time, and on top of that, on lightweight devices, executing 40 iterations is simply too costly. The good news is that the IEEE is updating the 802.11 standard that underpins Wi-Fi. They are now suggesting the use of a constant time hash to curve algorithm. They are prohibiting the usage of weak elliptic curves. They are preventing crypto group downgrade attacks, and they are now also enabling the offline computation of the password element. There are still some remaining issues in this update to the draft IEEE standard though. Namely, the message transcript is not included in the key derivation. This prevents a formal proof of the protocol, and it also increases the risk of implementation issues where a programmer may, for example, forget to defend against downgrade attacks. Another issue is that certain downgrade attacks are not explicitly addressed. For example, the downgrade attack to WPA2 is not addressed in the IEEE Wi-Fi standard. It is up to vendors whether to implement a defense against this or not. And currently we see that Android and the network manager of Linux implement a trust on first use principle, where if they connect it to a network using WPA3 once, they will not revert back to WPA2. Another potential issue is that these updates are not backwards compatible, meaning there is a risk that an attacker can downgrade an implementation from the updated WPA3 standard to the original WPA3 standard. So to conclude the talk, WPA3 is vulnerable to several side channel attacks. The countermeasures are very costly and difficult to implement. The good news is that the draft Wi-Fi standard is being updated, and perhaps the most important takeaway is that these issues could have been avoided if the advice of the IETF on CFRG would have been followed. Thank you for your attention.